Welcome to The Explainer. Today, we're going to get right into it and talk about force vectors. Specifically, how do a whole bunch of different forces all add up into just one?
So, let's start with a really simple question. You've got this hook, right? And it's being pulled by two different forces in two different directions. Where does it actually end up going? That's the core problem we're going to solve today.
And to answer that question, we're basically on a quest. We're looking for one single thing, what we call the resultant force.
You can think of it as the grand total, the final answer. It's that one single force that has the exact same effect as all those other individual forces combined. It tells you the final outcome of all that pushing and pulling. This is what we're looking for.
Okay, but before we can actually find it, we've got to get on the same page. We need to speak the language that engineers use, And it all boils down to knowing the difference between how much and which way. So, in mechanics, pretty much everything falls into one of two buckets. On one side, you have scalars. They're super simple, right? They're just a number, a magnitude, a size. But on the other side, you have vectors. And these are way more descriptive because they tell you two things, a magnitude and a direction. And believe me, that direction is absolutely key.
Yeah, so if you say something like 10 kilograms or 30 seconds, you're talking in scalars. There's no direction attached to that, is there? It's just an amount.
But force? Oh, force is the perfect example of a vector. I mean, think about it. It doesn't just matter how hard you push on a door. It matters which way you push it, right? Push in, it opens. Pull out, it opens. Push on the hinge, nothing happens. That direction is absolutely critical.
All right, so let's get into the nitty-gritty. How do we actually add these force vectors together to find that resultant force? Well, the first way we can do it is pretty visual, almost like drawing a picture. It's called the parallelogram law, and it really is kind of like drawing a little map. So you start by joining the tails of your two forces, A and B, at the same point. Then, from the tip of vector B, you draw a line that's parallel to A. And you do the same thing from the tip of A, drawing a line parallel to B. See how that makes a parallelogram? Well, that diagonal, the one that cuts right through the middle from where you started, that is your resultant force. It's a really cool way to see what's happened. But here's the catch, and it's a big one. This whole drawing thing is pretty neat for two forces. But what happens when you have 3, or 4, or 10? Can you imagine how messy that geometry would get? It becomes a nightmare of trigonometry really, really fast. So clearly, drawing isn't going to cut it for complex problems. We need something more powerful, more precise, something that can handle any number of forces without needing a giant piece of paper and a protractor. And this is what engineers actually use. And the idea is honestly, it's brilliant. Instead of dealing with all these weird angled forces, we just break them down. We resolve every single force into its simple up, down, and left-right parts. We call these rectangular components. It's exactly like giving directions. Instead of saying, go 5 miles northeast, you just say, go 3 miles east, then 4 miles north. So much easier to add up, right? And this table, this just shows you how powerful that is. Look, you just list out all your forces, you find their x and y parts, and then you just add. You add up the whole x column to get your total x, and you add up the y column to get your total y. All of a sudden, that messy geometry problem has turned into basic addition. It's that simple.
So here's the punchline. After all that simple adding, you're left with just two numbers, a final x force and a final y force. And from there, you just dust off your old friend, the Pythagorean theorem from high school math, and boom, you've got the final magnitude of your resultant force. It's just so elegant and so much more efficient.
And here's the best part. This whole component method is so powerful because the real world isn't flat, is it? It's not 2D. This method scales perfectly into 3 dimensions. Let's take a look at how that works. So, to get around in this 3D world, we need some signposts. Meet your new best friends, I, J, and K. These little guys are called Cartesian unit vectors. They're super simple. They each have a length of exactly 1, and they do one job. I points along the x-axis,
J points along the y-axis, and K points along the z-axis. There are 3D guides.
And guess what? The logic is exactly the same as it was in 2D. You just add up all the I components, all the J components, and now all the K components. You get your total for X, your total for Y, and your total for Z. And just like that, you can find the one single resultant force for any number of forces in full 3D space, no matter how crazy the system looks. Okay, so let's bring this all back home. Let's look at the actual step-by-step process an engineer would use to solve that problem with the hook from the very beginning.
This right here, this is the recipe. It's the 4-step process that is really the backbone of this entire field of statics. First, you lay down your XY coordinate system. Second, you break every single force down into its X and Y components. Third, you just add them up algebraically. And fourth, you use those totals to calculate the final magnitude and direction of that resultant force. This exact process is used to analyze forces on, well, everything, from massive bridges to the tiny bones in your body.
So when we talk about finding the resultant force, you really have two main tools in your toolbox. The drawing method, which is great for visualizing, and this component method, which is what you'll use for any real problem. It's just so much more powerful. Now, there are even more advanced ways to define a force's direction in 3D, but this component method, this is the fundamental building block for all of it. And sometimes you have an even more specific question, like what's the exact angle between two different forces, or how much of one force is pushing in the same direction as another? For things like that, engineers have more specialized tools. One of the most elegant is called the dot product. Think of it as a mathematical shortcut that lets us answer those tricky geometry questions without all the fuss. So there you have it. You now have the fundamental tools to start seeing the world, well, like an engineer does, as this incredible, invisible web of forces all interacting with each other. From the gust of wind pushing on a skyscraper to the tension in a single guitar string, these vectors are everywhere. And now you know how to figure out what they're all adding up to. So the only question left to ask is, what hidden forces are shaping your world right now?